These are notes for nuclear chemistry, and they are notes for worksheet 1. So nuclear chemistry, why do we care? A speck of plutonium, which would be dust size, can cause lung cancer. A grapefruit-sized ball of plutonium could take down a whole city. And the first death from human-induced radiation occurred in 1902. We wear lead smocks at the dentist to protect ourselves from radiation. And in the early 1900s, it was fashionable to drink radium water. People died of cancer. Some interesting facts. Radium became very fashionable to use in the early 1900s. It was placed in cosmetics, toothpaste, tea, and other tonics. It was also painted onto watch and clock dials to make them glow. And more than 100 of these dial painters died because they shared their paintbrushes with their mouths, or they licked the tips with their mouths. And once ingested, radium is stored in the bones and causes cancer. You could look at this website to find some examples of radiation poisoning. You could read about Eben McBurney Byers. You could read about Alexander Litvinenko. And some things we might want to talk about. What determines the chemical and physical properties of matter? The arrangement of electrons. During normal reactions, what happens to the nucleus? Nothing. The nucleus only changes during nuclear reactions. So radiation. Radiation comes in different types, from light to nuclear. Penetrating radiation from an unstable element is called nuclear radiation. There's an alpha type. There's the alpha symbol, which is a helium nucleus. There's beta, which is the same as an electron. There's the beta symbol. Gamma is a type of light. There's the gamma symbol. And positron is the same mass of an electron but an opposite charge. And there's the symbol. Why do atoms decay? Because the nucleus of some isotopes do not have the proper ratio of neutrons to protons. A proton to neutron ratio of 1 to 1.5 is the most stable for heavy metals. A nucleus will try to become as close to that ratio as possible by decaying. So let's look at alpha radiation. It's nuclear decay where 2 protons and 2 neutrons are released from an unstable nucleus. It's the most massive of all nuclear emissions. It can travel 4 to 7 inches in the air, and it could penetrate paper or a single layer of skin. Paper or a single layer of skin will stop the alpha rays. It's harmful if inhaled or ingested. And here's the symbol 4-2 and that alpha symbol, or you could write 4-2 in helium. Beta radiation is nuclear decay in which a neutron decays into a proton releasing an electron. Beta is the second most massive. It could travel 1 millimeter to 10 yards. It could penetrate several millimeters of thickness. It could be stopped by a layer of clothing, eyeglasses, or aluminum. And it is also harmful if inhaled or ingested. And here's the symbol 0, -1, and the beta symbol, it's a B with a long tail. Or you could use 0, -1, and the E, which is an electron. Gamma decay is nuclear decay in which a nucleus releases energy to become more stable. It accompanies almost all types of nuclear decay. It's the least massive. It has no mass since it's a form of light, photons. But it's the most penetrating. It can pass through the human body, glass, aluminum, and other materials. It can travel up to 1 mile in open air. It would require thick layers of lead, steel, or concrete to block it. It has 10,000 times as much energy as the photons in the visible range. The symbol is the upside-down ribbon and a 0 and a 0. No mass, no charge. Sources of gamma rays. You could find it in the soil, water, and meat in the form of potassium-40. It's present in iodine-131 through nuclear explosions. Cobalt-60, food irradiation used to gauge the thickness of steel in manufacturing, or the height of a liquid at a bottling plant. Positron, a particle with the same mass as an electron but opposite in charge. Very short life because it is destroyed when it collides with electrons. So again, it's the beta particle, but it's a 0 with a +1, or you could use the E, which is a 0 with a +1. And here's a chart to look at if you'd like to. Nuclide definitions. A parent nuclide is the nuclide undergoing decay. It's on the left side of the arrow or the equation. The dotted nuclide is the resulting product, and it's on the right side of the equation or arrow. So let's look at an alpha particle decay. So you have alpha particle decay, and we're writing it here as helium. So Bi decays into an alpha particle and into Tl. And you know how to figure this out because 207 plus 4 adds up to 211. And the bottoms must add up. So 83 must equal 2 plus 81. The left side must equal the right side. The tops equal the tops, and the bottoms equal the bottoms. And this one, so we have uranium-238. It breaks up into 4 plus 2, 34. 92 breaks up into 2 plus 90. And you can find TH by looking for number 90 on the periodic table. And there's the generic form of the equation. Beta particle decay results in a nuclide with the same mass number but an atomic number that is one more than the parent nuclide. In other words, a neutron is changed into a proton, and so the mass increases. So here we go. We have 10.4Be. There is the beta particle, and it changes into 10.5B. So 5 minus 1 is 4, and 10 plus 0 is 10. Here's another one. 234 equals 0 plus 234, and 90 equals 91 minus 1. There's the generic equation. Electron capture. When a beta or electron particle is captured on the left side of the reaction, gamma rays are produced on the right side. So there's the gamma ray. You just have to throw it in there when you have electron capture. So 59 plus 0 is 59. 28 minus 1 is 27. Look at 27 on the periodic table, and it'll tell you it's cobalt. There's the generic form. Positron decay or emission. The mass number is unchanged while the atomic number decreases by 1. So we have our boron, and here's the positron decay or emission. Decay or emission is always written on the right side. So 8 equals 0 plus 8. 5 equals 1 plus 4. There's the generic form. Gamma ray, high energy nuclide to low energy plus a gamma particle. Neutrons can react too. A neutron can react. The symbol is N with a 1 and a 0. So lithium, 6 plus 1, has to equal 7 on the other side. And on what is not written there is that you also have a helium particle. So if you write the helium particle, you have to do 4 plus 3 would equal 7 on the other side. And 3 plus 0 is 3, so the 2 plus a 1 must add up to 3. A series of decays. Most nuclei achieve a stable state through a series of decays, not just one decay. For example, uranium eventually decays into lead over many decays. So first it would break up into alpha and TH, and then TH is unstable and break up into the beta, the gamma, and Pa, and eventually, after many more decays, you'd end up with lead. Nuclear transformation is also called a transmutation, when one element changes into another element through a nuclear change. Lord Rutherford was the first to observe this. Irene Curie, which was Marie's daughter, transformed aluminum to phosphorus. New elements have been created by bombarding nuclei and particle accelerators. An example, element number 116 was created and only lasted 1.2 milliseconds before decaying. Those are the end of our notes for worksheet 1. I hope you enjoyed that.